All right, welcome to my lecture on the theoretical properties of the binomial distribution. So just to recap, the binomial distribution is captured by this density function. The probability x has little x successes is n choose x times p to the x times 1 minus p to the n minus x. Some people also write it like this, p to the x times q to the n minus x, where obviously q is equal to 1 minus p. Okay, so what do I mean by theoretical properties? So to be specific, the theoretical properties that we're going to calculate are going to be the expected value of x, known as the mean, 2, the variance, sigma squared, of x, which is also known as e of x squared minus mu squared. Okay, and the third one, which we'll actually begin with, is the moment generating function of the binomial distribution. Okay, and the moment generating function is the expected value of e to the t times x. And the moment generating function has one other very nice property, which is that the moment generating prime taken at 0 is the mean. Okay. Now, it has another one that will help us with item 2, but let's first start with the moment generating function. So one thing that I'd like to note is that a plus b to the nth power is this summation from x equals 0 to n. And here x is the index of n choose x times a to the x times b to the n minus x. Okay, so that's a fact that was on our calculus review. Okay. And it's also called the binomial expansion or binomial theorem, is this one right here. Okay, so let's start with the moment generating function. Okay, the moment generating function of a binomial is going to be this expected value of this e to the t x, which is calculated according to the summation from x equals 0 to n of this e to the t times x times p of x. But wait, for this p of x, that's binomial. So we can go ahead and plug in what calculates probability here. And what calculates probability for a binomial distribution is this: n choose x times p to the x times q to the n minus x. And now I'm just going to group things. I'm going to do some algebra. And I'm going to put these two terms together. Okay, so I'm going to have n choose x times p times e to the t raised to the x power. Algebraically, that's the same, and I'm going to have q to the n minus x. Well, wait, this whole formula looks very familiar to me, and if I just scroll up, oh, here's that calculus review fact right here, if I let A be this term, P e to the t, and B equals to Q, I get exactly this. That's going to be equal to A, which is P times e to the t, plus B, which is Q, raised to the nth power. Okay, and that is the moment generating function. So this thing right here, that's the moment generating function of a binomial. Okay. Now, here's going to be another fact that's very useful, and it's just this fact. The moment generating function taking the kth derivative, okay, so dx to the k, and evaluating at t equals 0 gives us the expected value of x to the k. Okay, let's prove this for k equals 1, i.e. prove e of x is going to be the moment generating function taking its derivative and evaluating at t equals 0. Okay, so if I just write out what the moment generating function is, it's this expected value of e to the t times x, which is this summation from minus infinity to infinity of e to the t times x times p of x. Okay, now if I differentiate, if I differentiate, and notice the variable here is t, if I differentiate with respect to t, this says that the moment generating function derivative with respect to t is going to be equal to the derivative of this. And now the only thing that involves t here is that term. So that's the only term that we differentiate. Okay, so when we differentiate this, we're going to get the summation from x being minus infinity to infinity of, well, the derivative of e to the tx is e to the tx, but now we differentiate what's inside, which is the exponent. The derivative of t times x with respect to t is just going to be x. So times p of x. Hence, the derivative at 0 means plug in t equals 0 of x times e to the t times x times p of x. This term becomes 1. So this becomes the summation from x equals minus infinity to infinity of x times p of x. And that is known as the expected value. And this applies for all functions, all probability density functions, not just the binomial. Note, when k equals 2, this says we get m double prime at 0 is going to be equal to e of x squared. Okay, so now let's just go ahead and calculate e of x. Okay, and if we calculate e of x for a binomial, we're going to start with mx of t is going to be equal to p times e to the t plus q raised to the nth. So mx prime of t, let's take its derivative. Bring down the exponent, we'll get n times p e to the t plus q raised to the n minus 1. Now we multiply by the derivative of what's inside. The derivative of e to the t is e to the t, so we're going to get p times e to the t, and q goes away because it's a constant. Now we're going to plug in 0. When we plug in 0, I'm going to have n times p times e to the 0 plus q raised to the n minus 1. Okay, times p times e to the 0. Now this is going to be n, and what we get inside here is p plus q, and p plus q is 1 times p. So at the end of the day, we get n times p, and hence the mean, which is e of x, that's equal to n times p, and that's where that formula comes from. Let's calculate the second derivative, okay? The second derivative can be a little bit more complicated. M double prime of x evaluated at t. Well, we're going to use the chain rule again here, as we did the first time. N times n minus 1 times p e to the t plus q raised to the n minus 2, okay, times the derivative of the inside, which is again p times e to the t times p times e to the t, okay. So notice we're using the chain rule, but because there's also this multiply sign, we have to use the product rule as well. So that was what we get when we differentiate that first term, n times p to the t plus q to the n minus 1. So now we leave that alone. N times p e to the t plus q raised to the n minus 1 gets left alone. And now we multiply by the derivative of p to the t, which is itself. Okay, that's the second derivative. Let's evaluate this at 0. Remember, e to the 0 is 1. So we're going to have n times n minus 1 times p times e to the 0, that's 1, plus q to the n minus 2 times p times e to the 0 times p e to the 0 plus n times p e to the 0 plus q to the n minus 1 times p e to the 0. Now let's do a bunch of simplifying here. We're going to have n times n minus 1 times p plus q, that's 1, times p squared, plus n times 1 to the n minus 1 times p. So now we have more simplifying. This will be n times n minus 1 times p squared plus n times p. Okay. Well, that's great. Let's see what this says. It says the second derivative, that's with k equals 2, is e of x squared. Okay. Okay. Now, let's rework this a little bit. And now let's notice that the variance of x, that's going to be that e of x squared minus e of x quantity squared. Okay. Well, e of x we have right here. That's n times n minus 1 times p squared plus n times p minus e of x, that's n times p quantity squared. And now let's simplify this. So I think we're going to have n squared minus n squared p squared minus n times p plus n times p minus n times p quantity squared. And hold on a second. This one is squared. Okay, so great. That was just a little bit of an algebra mistake from one line to the next. So n squared p squared, that cancels. And what I have is n times p minus n times p squared. And we're just going to factor this out. It's going to be n times p times 1 minus p. And when we simplify this, this will be n times p times q, and that's the variance, okay? That's also denoted by that symbol. So standard deviation, that's going to be square root of n times p times q, and that is denoted by sigma. This thing right here, the variance, it has units squared. Whatever the units of x are, it's squared. And this standard deviation has the same units as x. So a lot of people prefer the standard deviation because it's not units squared, it's the original units we started with, and that's much more useful when interpreting the standard deviation. Okay.